Alrighty, time to do 10-4. I actually did this whole video and somehow didn't record it, so I'm kind of crabby that I'm doing it again. But let's roll. All right, we are going to talk about union and intersection. If you remember the good old days of doing Venn diagrams, you'd be like, oh, hey, I have this category and this category, and like this might be A and B. Where they overlapped, we called the intersection of them. So that's kind of going to be the terminology we're using. And then when you talked about all of it together, that was the union of the two pieces. You could be an A or B for the union, but when you were doing the intersection, you had to be in both. So it was like A and B or both or your overlap. So union, which was notated like that, is going to be the or, like you could be in A or B. Intersection, which is notated like that, you had to be in both categories. You have to be part of the overlap. You have to be in one and the other. So and or, you would have kind of talked about that in the past. So the reason I bring it up is we have this formula. This formula is the one you're going to use any and every time you are supposed to find the probability of something that's, hey, what's the probability that it's this or that? Now, it looks like there's two formulas, but if you can see, these are the same, these are the same, these are the same. So the second formula is exactly identical to the first one, except for this last part. So let's break this down a little bit. What this is saying is if you have the probability of one thing or the other, then you can find what you need by taking the probability of the first thing plus the probability of the second. So you're going to add them together when they're OR problems, but you take away the and or the intersection. So you're taking away the probability of A intersecting B, and what that means is you're taking away the overlap. In this one, there simply isn't any overlap, so that part of the formula is gone. When there isn't any overlap, we call it mutually exclusive. Disjoint, we don't use that as much. But mutually exclusive means they exclude each other. They do not have any overlap. So when you go to do like the number of things that are in A and also in B, that's going to be none. So if I have face cards and number cards, they don't overlap. You never have a card that's a face card and also a number card. Red and black, you never have a card that's red card and also a black. So they are mutually exclusive. Even in odd numbers, you never have a number that's both even and also odd. So that's considered mutually exclusive. So I honestly never think of this as two formulas. I use this as my OR formula anytime I see OR. And then I just ignore the last part. I don't subtract the overlap if there's no overlap, because you're basically subtracting literally nothing. All right, let's do some math with that formula. A card is randomly selected from a deck of 52. What's the probability that it is a 10 or face card? So up here in my formula, 10 is like my A, and then face card's like my B, my second thing. So I'm going to break it down and say, what's the probability of getting a 10 plus the probability of getting a face card minus the probability of that a card is both? Well, you can't be both a 10 and also a face card because face cards are Jack, Queen, King. So this is going to cancel, or you can ignore it because these are going to be mutually exclusive. If you are a 10, great. If you are a face card, great. But there's no such thing as a card that's both. So all I have left is this part of the formula. Probability of getting a 10 is 4 10s out of 52. Probability of getting a face card is 12 face cards out of 52 cards. I don't reduce till the end because then they always will have the same number on the bottom, and I can just go ahead and add the tops. And I'm going to get 16, which will reduce to 4/13. So that's a legitimate answer. Or if you like to have a decimal instead, it's about 0.3077 if you round it off. So that's this or this. A card is randomly selected from a deck of 52. What's the probability that it is a face card, or spade. I'm going to break it down according to my formula. I do the probability of the first thing, which is a face card, plus the probability of the second thing, which is a spade, minus the probability of any overlap, any cards that are both. And in this case, they're not mutually exclusive because you can be both a face card and a spade. Jack of spades, queen of spades, king of spades are both. So when you go to count up your face cards, you're going to have 12 out of 52. When you go to count up your spades, you're going to have 13 out of 52. However, the jack, queen, and king of spades got counted as face cards and got counted again as spades, so you have to take away those 3 cards. And those 3 cards are the ones that are both things. They are both spades and face cards. So because I have a common denominator, I can just do the math on the top. So 12 plus 13 is 25, minus 3 is 22. That reduces to 11 over 26. And again, if you prefer to do a decimal, you're going to have, in this case, 0.423. So I would say either this fraction here or that decimal. Now this next one's tricky. You have 200 students, that's your total. 13 are either in varsity athletics or honor roll, there's a key word. There are 74 seniors who are athletes, 51 that are on the honor roll. What is the probability that a randomly selected senior is both? So we're still using that formula, but what we don't know is different. So it's about saying, hey, what's the probability? You've got athletes or honor roll. So that's going to be the probability that they're an athlete plus the probability that they're on the honor roll minus the probability that they're on both. So what's tricky about this problem is the both is what we're trying to find. So this thing is going to be my unknown. It tells me that out of 200, 113 are in athletics or the honor roll. So my or is 113 out of the 200 kids. How many are just athletes? 74. So 74 out of the 200 kids are athletes. 51 out of the 200 kids are on the honor roll. So what is it says, what's the probability that a randomly selected senior is on both? Well, the both is the number we don't know. That's that last part of the formula that got subtracted. So this looks daunting, but they all have the same denominator. So I have a common denominator. So I can just solve the top equation. So the top equation is 113 equals 74 plus 51 minus x. So we've been in math long enough to know that we're going to add these together and get 125. Then we're going to take away that 125. And we're going to get negative 12 equals negative x. So positive 12 equals positive x. So it asks us for the probability. So we're saying 12 out of the 200 kids are both athletes and honor roll. So if you do 12 over 200 as a decimal, you're going to get 0.06. And if you do that as a reduced fraction, you're going to get 3 over 50. So either one of these is the right answer. It's just tricky because the thing you didn't know was the last part of the formula. Okay, mutually exclusive. Which ones are mutually exclusive? Can you be a heart and also a spade? You can't be both. And whenever you can't be both, then that is mutually exclusive. Can you be a heart and also a face card? Sure, Queen of Hearts. So that is not mutually exclusive. Can you be both a spade and a red card? The answer is no, so these are mutually exclusive. So if you ask yourself, hey, can you be both a heart and a face card? And the answer is yes, then they are not mutually exclusive. They do not exclude each other. They include each other. They include cards that are hearts and also face cards. All right, the last concept is complements. They're like a special kind of mutually exclusive. You can't be both things, but a complement is going to be the rest of the options. So it has to use up all the options. So it's kind of like the not of the other thing. So if you're saying, oh, hey, what's the probability that you're a 7? The complement is the probability that you're not a 7. So if one of them is, hey, here's the probability that it's sunny, the other is, well, what's the probability that it's not sunny? But it's either sunny or it's not sunny. So that takes up all the options. A card is either red or black. So that takes up all the options. So that makes it those things complements. When you have like a regular event, this is like the thing happens. Like, oh, I'm going to get a face card. I'm going to get a 7. This is that it does not. So that line means complement. And they're going to add up to a probability of 1 because that's all you get. So if you're looking and saying, hey, here's my sample space, and this slice is representing that something happens, that's my event, then the rest is going to be the complement of that. And together they make up the whole entire thing. So you can't say like spades and hearts are complements because spades and hearts don't make up the whole deck. You also have diamonds and clubs. And so it has to like fill in all the gaps and take up all the spaces. So if I look here, some examples, these are not asking, these are telling me these are complements of each other. This is supposed to be red and black. That is the whole deck. If you have a deck of cards, smack dab down the middle, you got a red half and a black half. That's everything. Even and odd numbers. It doesn't have to always be half like these are, but it's true. A number's even or it's odd. There's no other options. And then number and face cards. So here they wouldn't be even because you only have 12 face cards and then the rest are number cards. But that's all you are, like the whole entire deck. Everything is either a number or a face card. So those are complements. This formula up here, I sometimes just think, okay, if I know the whole thing, I can take away the probability of something happening, and that will give me the other complementary probability. So instead of adding them up to 1, sometimes if I know one of them, I'll just take it away from one to find the other. Like if the probability of getting heads is a half, then the probability of not getting heads is 1 minus a half, which is still a half because that's tails. So let's see. When you roll the dice, there's 36 outcomes. Find the probability that the sum is not 6. So that's the probability that it's not 6. But if you look at the card, like the ones that are equal to 6 when you add them up, there's like 1, 2, 3, 4, 5 of them in a diagonal. So 5 of the options are 6. Which means instead of counting all the other options, I can just be like, well, 36 minus the 5 that are 6 would give me 31 that are not 6. So I would have like 5 options out of 36 plus how many out of 36 adds up to 1, which is 36 out of 36 from my little formula up here. Well, there must be 31 out of 36 that are going to be have a sum that is not 6, and that doesn't reduce. Okay, a sum less than or equal to 9, so it could add up to 2, 3, 4, 5, 6, 7, 8, or 9. That's a lot. So what I'm going to do instead is be like, hey, the ones that are not less than or equal to 9 there's going to be 6 options out of 36 that are not less than or equal to 9. So the ones that are going to have to be the rest. So the ones that are less than or equal to 9 will be the rest. So if there were 36 and 6 of them are not, then 30 of them are. And I can reduce 30 over 36 to 5/6. And if you really love yourself a good decimal, you could divide that out and get 0.833. Sum is less than 12. Okay, so for sure I don't want to count those, because if you look, there's only one that's actually 12 and all the rest are less than 12. So the sum is less than 12. I don't want to count all of these. So what I do is I just go, okay, well there's one that's not less than 12. So that means because they're complements, the rest are. Well, the rest would be 36 minus 1. So 35 are in that category of less than 12. So 35 options are less than 12 out of the 36, and that doesn't reduce either. So that, what it's designed to help you do is if the part you need is really huge, it's easier to count the small part and just take it away from the whole section. So hopefully that helps and doesn't confuse you. Good luck. Bye. You need to go outside, Dolly?